I'll jump with the first question. So if you have others, feel free to post them in the chat or get ready to pose them for Ryan. I caught one point you had. I mean, this was super comprehensive and great to have the slides as well and have the recording so we can go back to it. This is I think a detail, but I noted how you mentioned that waypoint navigation that's not autonomous. Can you expand more on what you mean by that?
Yeah, I think the to me autonomy is a little bit more more broad than that, and generally, if you're doing waypoint navigation, you're doing planning offline, and you're feeding a list of waypoints to a robot, which then basically goes from point A to point B in kind of the straight line path, connecting those waypoints. And so I would argue that's kind of what I would call semi-autonomous, meaning that you use your sensors, either dead reckoning or some augmented system, to go from point A to point B, but you're not determining A and B kind of on the fly. And so when I think of waypoint navigation, I think of that being a kind of a pre-processed step that's then fed to the robot. Whereas the autonomy part would come in by saying, I'd like you to go survey this area, and then have the robot define how it's going to be surveyed, what happens next, and not have a pre-programmed plan, but actually adapt in situ and really walk that line of explore versus exploit. And we do this very well as humans. When you go into a new city and you're very interested in learning about that city, you walk in and you don't have a preset path to walk. I mean, unless you go to Boston and you walk along that Colonial Trail or whatever that is. You just kind of explore the city for what the city is, and this is the autonomy that we have as humans that we'd like to impart on the robot. So explore the environment until you find something of interest that may be predefined, and then exploit that for the interesting artifacts or interesting science that it is, and then report back that information. So when I stress autonomy, I'm thinking more of putting the robot out and just turning it on and saying, go, and here are some interesting features I'm looking for. Please go figure out where they are and then come and tell me. As opposed to giving it a waypoint list and having it follow that. I don't really consider that to be autonomy.
Super. Thank you. Thanks for explaining it so intuitively as well. Wallace had a question in the chat wanting to know more about your SLAM techniques, and he's familiar with those for aerial robotics, but was quite curious to learn more about how this is applied in underwater robotics and what the main challenges are. And for those who might not be familiar with SLAM techniques, maybe if you could say a few words about that before answering the question.
Sure. So SLAM is simultaneous localization and mapping. And most commonly, SLAM is done with visual data or image data, either through a camera or through a video recording device. And essentially what you're doing is, say you have a video camera on board, you're recording pictures at about 30 frames a second, and so what you're doing is, as a vehicle moves along, you're building up a map of the environment. And SLAM is basically a way, or is the fundamental way of developing what we call loop closures. So what happens is, as you, in simultaneous localization and mapping, so as you're gathering data, you're mapping, but you also want to localize yourself in this environment. So you have no idea what the environment looks like, but you've got a bunch of image data, and all of a sudden, if you actually come back to the place that you started, you should be able to match features within the images that you've recorded that say that you are at the location where you started, or that you have been at that location before. We call that a loop closure. And generally, when you have a terrestrial or aerial or underwater platform, you're navigating with kind of an augmented dead reckoning. So you're looking at odometry, you're looking at inertial navigation, or just compass and thruster power or something like that. And those have high amounts of drift. I mean, the sensors drift, the estimation techniques are really bad. If you're using an IMU, you're double integrating to get position estimates, which, you know, there has a whole bunch of error in it anyway. And so as you move, your state estimation solution increases without bound. But if you actually close the loop and come back to a place that you have seen, quote unquote, before, then you're able to correct your odometry and bring that, bring the error back down on your state estimation solution. So that's what SLAM is. In the underwater environment, it's exactly the same as the aerial environment, except the challenges here are you can really only do it in shallow water because of light. So the camera actually, you know, needs a lot of light in order to work. The other part of it is that in a lot of places, it's very hard underwater to discern if you're actually back at the same place again. A lot of the features are hard to pick out, or almost actually too feature rich to say that we were back at the same location. Lighting changes, different hues, blurriness, and different, you know, sand covering different stuff and obscuring different features makes it really challenging to do this underwater over long periods of time. You know, we've seen in cars and on aerial platforms that, you know, the SLAM solution, you can go out and you can drive around for months and actually have a really good, reliable solution just by SLAM driving around a town. You can even do it with a monocular camera. You don't need anything fancy. It's almost really a solved problem. The issue is actually with collecting visual data underwater is where that challenge comes in. Did I answer the question enough?
Super. Yes, it looks like on chat, Wallace just said perfect.
Cool.
We have about 10 minutes left, and I wonder if there are 2 points that maybe would be worth learning more from you about is the machine learning aspect in terms of, I believe that's to make sense of the data being collected. I know it's a broad question, but can you share more about what kind of techniques specifically you're using and how that's making a difference and why they're so useful? And if we have time to bring up a conversation that you and I have had on another use case for aquatic robotics, which is cargo delivery. Could we have autonomous boats or underwater vehicles deliver medicines, foods, and so on to different islands and so on? So I wonder if you could maybe speak to both. I know it's a lot, so feel free to choose if you have to.
Well, I'll quickly touch on the learning aspect. You know, I think since Andrew Ng developed deep learning, was it almost eight or 10 years ago now, that has fundamentally changed the way we do deliberation, the way that robotics is kind of performed. You know, it started with machine learning that will actually, you know, give you a good start there. And basically what you're doing is you're taking a huge dimensional space, so a lot of data, and you're trying to form correlations. And correlations between these variables in a nonlinear sense. So how is everything related, and can you tease out relationships that would not be obvious through any other means? Now, fundamentally, that's kind of machine learning. When you go into deep learning, actually what's happening there is you're not actually looking for the relationships between these variables, but what you're finding in very high dimensional spaces, and the easiest way to say it is you're finding the unit vectors that compose everything that you've seen, or everything in the space of data that you're looking at. Now, here's the example, and everyone loves this one. If you let a deep learning engine watch, say, 50,000 hours of YouTube, one of the unit vectors that it comes up with is the face of a cat. Why? Well, there's a lot of cats on YouTube, and if fundamentally you were going to describe or be able to construct a YouTube video, you would need the prior of a cat face to do most of those videos. It also came up with kind of a human-like face because there's a lot of people on YouTube. There was an object that kind of looked like a tree, because there are a lot of nature scenes on YouTube. But fundamentally, what the deep learning architecture does, it's based on a neural network, and essentially allows you to grab the basic architectures of that data. So essentially, if you look at Cartesian space as R3, what are our unit vectors? It's 1 unit in X, 1 unit in Y, 1 unit in Z. And if we combine linear combinations of these unit vectors, we can go to any point in space. If you take a high-dimensional data set, which could be all the physical water parameters in the ocean, optical and non-optical, so temperature, salinity, depth, chlorophyll, turbidity, et cetera, then what you can do is you can start forming these basis vectors for how to construct all of the possible scenarios that could exist in the area you're studying or in the entire ocean. And so fundamentally what it does, it gives us a basis for high-dimensional data sets. And I'll let your imaginations run on how that can be used, as I'm actually getting my imagination stretched at the moment with this project I just started that I mentioned earlier.
Great, thanks so much. Ryan, do you want to close up by just speculating on the possibility of using aquatic robotics for transportation? Sure.
I think that aquatic robots for transportation, especially in the context of medical delivery, is a really novel and innovative and practical technique for this. Some of the primary questions that arise out of this generally go in or dovetail into kind of the platforms I presented as to what persistence is needed, how long do these things have to transport, and what are the power requirements going to be. I think fundamentally really what it comes down to is whenever you're transporting something, and this can be an autonomous ship or a manned ship, is what kind of waters are they going through, and what kind of hostility might they meet based upon the cargo that they're carrying. So if you have an unmanned vessel and it is carrying a very sensitive package, it's probably going to be very easy to catch that vessel by sneaking up on it, so to speak. But as long as I think the humanitarian effort for this one, as long as we're not trying to push things into the realm of transporting very valuable or widely known things that are highly valuable, I think it could be a very reliable resource, very easy to deploy, and very straightforward.
Perfect. Well, thank you very, very much for your time, Ryan. It's great to have an expert be able to give this kind of overview and in-depth also technical insights as well. So thanks very much for joining. We'll make the recording available as well to everyone. And thanks to those of you who were able to make the time to join us as well. We'll be looking to do another webinar in November. We're hoping that our Flying Labs coordinator in Tanzania will be able to share with us some of the work that he's been doing as part of the Flying Labs and what's already been done in Tanzania. So we'll provide you with an update on that in coming weeks via the Google Group. So thanks again, everyone. Have a great day and a great rest of the week.
Thank you very much for having me. It was great to talk with you all, and I look forward to any questions you might have. Patrick's got my email, or just reach out.
Super. Thanks again, Ryan, and thanks again, everyone. All the best.
Bye.
Bye-bye.